Part C of Module 2, Brute Force Method, C.1, Introduction. First, so let me give you a brief description of this simple method. Yeah. From the name, you can see it's a straightforward, relatively simple method. So let's look at the properties of brute force method. First, it is a straightforward approach. So you do not need to use any specific, special, arranged, that kind of method. Just do based on the direct way to solve the problem. So the straightforward approach. Yeah. And you can always apply it. So usually given a problem, you can always try to use the brute force method. Okay? Solve it directly, okay? Without using any special techniques. Yeah. And usually people do in this way. Yeah. And in general, it is not the best algorithm. Yeah. So for most of the time, you cannot get the best solution using this way in general, but it's possible in some small situation. So usually for relatively simpler problems, the problem itself quite easy, so you can solve it. Just use the brute force method, you can still get the best solution. That's possible, but not very common. Yeah. All right. It is usually used as the starting point for more advanced algorithms. So usually we do in this way. At the beginning, we do not have any idea how to solve the problems. So at the beginning, people like to try using the brute force method to get a little more understanding. Yeah. After that, so then when people understand the problem more and more, they try to use better algorithm to solve. Yeah. So usually we use brute force method as our starting point. Yeah. Definitely we are not satisfied with this result most of the time. The efficiency difference between the brute force method and the more advanced algorithm could be huge. Okay, could be huge. Yeah. Especially for relatively hard problems. So most of the time, the brute force method cannot give you a good solution. So you need to try to use more advanced algorithms. As a result, the efficiency difference could be huge. Here, we already have that example. Here, let me bring this. The polynomial evaluation problem. We did two methods. The first one is the brute force method. Okay? So most people like to use because they only know that method, right? The second, we use that Horner's rule. That Horner's rule, the difference, the improvement is huge. Yeah. I show you some example and compare the difference. Remember, 5.8 days versus 1 second. That big, that difference. Yeah. So you can imagine the algorithm efficiency difference, really big. Yeah. All right. So after this simple description, next, we like to use it to solve a problem. Okay. All right. The problem is an old one, sort and array. So we revisit it. Yeah. Remember, we use selection sort to solve this problem before. Now we want to solve it in the second time, revisit it. Yeah. Given array, how to solve in ascending order. Yeah. All right. For the older problem, we try to use a new way to solve it. The question is, why we need to solve it another time, right? So usually when people solve a problem, they never want to try using a different way to solve it. Yeah, many people like that, yeah, right? But for this class, for some of the important problems, we need to solve it many, many times. So this sorting problem, we will solve it many, many times. Yeah. Why we do it that way? Yeah. Here, I want to explain a little bit why we want to do it that way. Our view on this particular situation, why one problem, people still want to solve it many, many times. Yeah. First, when we look at a problem, we treat it as a carrier of a set of thinking methods. When we solve a problem, we need to use our thinking. We need to use special thinking methods. So now the problem carries several different thinking methods. That is our view on it. Yeah. That result in different solutions. Yeah. The reason we look at it in that way is, let's think in this way. Because, for example, we know our thinking methods are important, are valuable, right? So there are several thinking methods, 1, 2, 3. Very important, very valuable. Later, we need to use these 3 methods to solve other real-world problems. But the problems, how do you carry these 3 thinking methods, right? These 3 methods, not like 3 different objects, 3 apples you can carry, right? The thinking methods, not like apples you can carry. Okay, so nothing can carry them in a usual way, right? All right, so now here we have this problem. Okay, we have this sorting problem. This sorting problem carries those 3 different thinking methods. How about that? Okay? When we talk to people, so when we try to explain a special thinking method, we need to grab that particular problem here and give it to the other people, then explain the thinking method inside that problem. That's our view. So that's why. Yeah. So we like this problem because it carries 5, 6, 7 different thinking methods. All right. Yeah. The thinking methods are important to help us solve other problems. Yeah. So that's the value. Yeah. Later, so there are many other new problems in the real world. How do we solve them? Oh, we learned some methods before related to this particular problem. So let's take part of it, modify it, then apply it to the new problem, and we get a solution. That's the typical way we solve real-world problems. All right, yeah. A view based on a special property. So now we try to solve the problem. Okay, now we want to get started. How to start? Now, so let me give you another frequently thing we need to do. try to find special property in our current problem. Okay? Yeah. If you can find a special property, then you can try to take advantage of this nice property. So then you may come up with some nice solution. All right. Here, let's try to find a special property from our problem. Observation. This observation step, very important. You try to use your sharp eyes, try to dig some very important property from the problem. All right. What is that property in our current problem? Sorting an array. What is the property? We need to find it. Okay? Yeah. We need to use a different view to find it. Last time we found one, right? Last time we found one. But this time we will use a different view to find a different property. Yeah. All right. So let's try to do it. Okay? Yeah. This is our general array. Okay? Yeah. Given the array. Yeah. Now let's try to make a very close observation on it. Okay? All right. If we look at two adjacent elements in the array, okay, yeah, and if this array is not sorted, suppose the array is not sorted. If it is sorted, then it's done, right? We don't need to work on it. But if this array is not sorted, what property can we see here? If it is not sorted, we can find two adjacent elements that are out of order. Out of order. Because we want to sort it in ascending order, but these two elements violate that ascending order, so descending order. Okay? The second one smaller than the first one. That's the property we observe. Right? Yeah. So now we want to explore this property and find a new solution. Yeah. All right. Observation for critical property. That is our critical property we found. If the array is not sorted, there must be two adjacent elements, right? Two adjacent elements that are out of order. So that's the critical property. Okay? Yeah. All right. Based on that, okay? Yeah. So this problem, here I give you the reference in the textbook. So you can study these pages in the textbook. Yeah. All right. So now, to study this property, out of order property, we want to introduce a new concept about this out of order, because we want to create a formal concept, formal terminology to describe this out of order behavior. So we use this inversion concept. What is inversion here? Okay. A pair of elements, AI, AJ, okay, a pair, not necessarily adjacent. So here, this is adjacent, right? But when we talk about a pair of elements, you can jump, right? Yeah, this pair, okay? Yeah, not necessarily adjacent elements. Yeah. It's called an inversion if I less than j and AI greater than AJ. Yeah, that's the inversion. Okay? The two elements could be far apart, different locations. Yeah. From the subscripts or from the indexes. The second one has larger index than the first one, but the second one has smaller value than the first one. That is inversion. Yeah, so this simple concept can help us describe how far a given array close to the sorted array, right? So here you can see the more inversions an array has, then you need to do more work to make it sorted, right? Yeah. So that's the, observation property we explore from our current problem. Yeah. Next, now we try to rewrite the critical property we observed using this new concept, inversion concept. Okay. Yeah. If the array is sorted, is not sorted, right? Not sorted, there must be an inversion. Yeah. Now we do not use that out of order phrase, we use this inversion concept. If it is not sorted, then there must be an inversion somewhere. Okay? Yeah, that's obvious. If there is no inversion in an array, it must be sorted. That's simple. Yeah. All right. But here we want to modify it to a better version for us to find a solution. So what's that? If the array is not sorted, there must be an adjacent inversion. So if you look at the beginning of our analysis, this pair of elements gives us adjacent inversion. So the first statement, we didn't mention if the inversion is adjacent or not, but our second improved version, we emphasize adjacent. What's the difference? Why this improvement is more important? The reason is simple. The reason is we change from a global view to a local view. The first version, we use global view. There is one inversion. That inversion could be a global inversion. Okay? Two elements are far apart, distributed globally, right, with respect to the whole array. So that is a global view. To fix that global inversion, that is much harder. The cost is much higher, right? Fix a global inversion. Now we change it to local inversion, local view. Yeah. So think about fixing a local inversion. Is it much easier? Yeah. Adjacent inversion, if we want to fix it, very easy. Global inversion, very hard. How to find them, right? After you find them, then you fix it. But the problem is, it is not easy to find global. The cost is high. The cost is much higher than only check the local inversion. Yeah, that's the main point. If you understand as deep as this, then the solution is very close. Yeah. All right. How to fix it? Yeah. So now we identify the problem, local inversion problem. So how to fix it? Yeah. How to fix a local inversion? Swap operation. You just do one swap, you fix a local inversion. That's simple. Yeah. Although you can say we can fix global inversion with a swap, the harder part is how do you identify that global inversion, right? How do you detect? Yeah. That will be costly. Yeah. All right. Next, implementation idea. Yeah. how to implement it. Yeah. All right, so our goal, we want to remove all the local inversions by local swaps. If you can do that, the whole array is sorted. If you can remove all the local inversions, the whole array is sorted. Okay. Now, the procedure. Step 1, start from the first element for each scan. So we scan it. We will process in many rounds. Every time we start from the first element, we do scan to fix the local inversions. Do swaps one by one from left to right. Okay, adjacent. So when we do scan, we fix local fix local inversions one by one from left to right. Okay, if necessary, because many times we do not need to fix. If there is no inversion, we do not do any swap. Okay, so if necessary, then we do a swap operation. Number 3, start at the first in-place element. So this step, we need to do further analysis, because you may not be able to understand this step at this point. We need to get more information to see it. So our next slide, we explain this step. All right. Now, in this slide, so let's try to understand step 3. First, all right, so look at every time when we do one scan, can you try to imagine what result can we expect? There is one element in place for every scan, in place. So I hope you still remember this concept. So there is one element at its right position when the whole array is sorted. That is in place concept. Okay. So when we do one scan, we can 100% sure we put at least one element in place. That is the first step. Why? So let's try to understand this step. Okay. So we do adjacent element comparisons. If there is a swap, we fix it, moving from left to right. Okay. All right. After one scan, can we claim we place the largest element at the end? Can we see that? Because think about, there is a largest element wherever it is. When we do local swap, comparison swap, the largest element will always move to the next one, always to the next one, until it reaches the end of the array. Okay. That observation gives us this statement, the largest. There is one, so this one actually is the largest one. Okay, so that's simple. All right. So, but after we place that largest element in the end of the array, at the end of the array, the next time we do not need to look at it. Okay, the next round, we remove that element from the consideration and do the local fix from left to right without including the previous largest element. How about that? So that's our next. The in-place element of each scan appears at the end of the current array. So with that, the The current array is a subarray that excludes all the in-place elements. If we already place some of the elements in place, now we don't want to touch them the next round. Okay? Yeah. We have them, so we leave them there. We do not want to touch them. Okay? We don't want to waste our operations to process those elements that are already in place. Okay? So that is our last stop at the first in place element. Okay? Yeah. There is a, all right, at the end of the array, okay? At the end of the array, yeah. Remember, every time we put one element in place, next time another element in place, another element in place. So we grow this in-place block. So we have the in-place block. Okay? Yeah. Every time our subarray, we stop when we hit the first in-place element in the block. Okay? So that is the meaning of this step. Yeah. That is the meaning of the step. Although in this small place, we couldn't give more precise description, yeah, because actually it is a little confusing, yeah, if we do not explain, if we do not use a lot of words to explain, a little confusing, yeah. All right, yeah. So now, when we do these steps, so now you can see the problem can be solved. Okay, yeah. Now, so we treat the problem can be solved. Yeah, so we can write, pseudocode program to implement the detailed steps. Yeah. Now we do visual imagination. Okay, visual imagination. Now, so let's take a look. Visually, what do we get? The swarm looks like a bubble moving to the right. Moving bubble from left to right. The swap operation. So that's why we call it a bubble sort. Yeah. You may have heard of this name, bubble sort. Now we do some very deep analysis on this algorithm. Okay? Yeah. And for the efficiency analysis, very similar to the one we did for the selection sort. Yeah. So here I do not need to repeat it. Yeah. So you can easily do it for the bubble sort efficiency analysis. Yeah. But for the last step, I want to ask you one question. What is the basic operation? Remember, when we try to do the efficiency analysis, we need to look at the basic operation. Here, what is the basic operation? Comparison or swap? We know swap is very important for this algorithm. But how about comparison? Which one we treat it as a basic operation for this algorithm? The answer is comparison, not a swap. Why? Because the comparison, it happens every time when we check two of the adjacent elements, we need to compare. Okay? Do we need to do swap every time? No. Remember, if necessary. Okay? Sometimes we do not need to do swap. Okay? But we always need to do comparisons. Every time when we check for the inversion, we need to compare. So that's why we treat compare as the basic operation. If you use the swap, then your analysis will not be precise. Why? Because if the array is already sorted, you do not use any swap. That's the best case, right? You do not use any swap. So then your swap number is very small. But even an array is sorted, you need to do comparisons. Still, from beginning to end, many rounds. So that's why we need to focus on the comparison part. All right, so that's the introduction part.